Okay, so first of all, let's review what we learned in last class. So in the last class, first we talk about the quantum number. We talk about quantum number, and we already talked about the quantum number is four groups of a number. We have n, l, m sub l, and m sub s. So if we have the full number all together, then they give us the address for any of the electrons in the orbitals. Okay, any of the electron in the orbital. So n is the primary quantum number. The n could be from 1, 2, 3, 4 until infinity. But in most of the cases is 1 to 7, right? And the L have to be smaller than n. And L is talking about what kind of the orbital it is. If it's 0, that's S. If it's 1, that's P. If it's 2, then that's D. If it's equal to 3, then that's F. So L generally only those options, right? Only those options. But the L must be smaller than 1 because the L have to be from 0 to n minus 1. I mean, there's no way for L equal to n. Okay. Then if we have n and L all together, generally this one will give us a subshell, right? Like a 2p or 3d. The 2p, n is just 2 and p is 1. So 2 and 1 is talk about is 2p. And 3D, then that's a 3 and a 2. That's 3D, right? If we talk about the 2s, then that means it's 2, 0. This is 2s. So the first and second quantum number telling us subshell, what subshell it is. M sub L is talking about which orbital in that subshell, which orbital in the subshell. And M sub L is equal to negative L to 0 to positive L. So they give us the several numbers. If the L equal to 0, then that's M sub L can only be just 0. M sub L, L equal to 1, so M sub L give us 3 number, negative 1, 0, and positive 1. So each of the number represents one of the box, one of the orbital. L equal to 2, M sub L give us 5 number. That represents the 5 orbitals in the D. And L equal to 3, they give us 7, which is represents each of the orbital in the F. Okay, so this is what they related to each other. The last one is just a spin quantum number, which is we only to have 2 electrons in the orbital, spin up and spin down. So the only just a positive 1/2 and a negative 1/2. So spin up and spin down. We're going to, so those two just refer which electron in the orbit, in the orbital. That's it. Okay, so we combine those 4 quantum numbers together, they narrow down to telling us which orbital, what's the address for the certain electron. Okay, and also last time we talked about the periodic trend. The periodic trends, the first one is the atomic radius. Atomic radius in general, from top right to the bottom left. Okay, top right to the bottom left, top right part is the smallest. And the bottom left is the largest. the atom. It's the largest atom. But here we're not including the noble gas, okay, not including noble gas. So in another word, the smallest one should be the helium. I think helium is the smallest, but fluorine, not including the helium and the hydrogen, fluorine is the smallest. Because the neon is bigger than the fluorine. So if we talk about the trends, not including the noble gas, okay. So this is from the smallest to the largest. This is atomic radius. We also talk about the other three. One is called the ionization energy. Ionization energy, and we call another one is electron affinity. And then electron activity. So those three has the same trends. They have the same trends. Top right is the largest. They have the largest ionization energy, largest electron affinity, and the largest electron activity. And bottom left has the smallest. So this is the trends. But general, a lot of people got confused then where we got these trends. This trend actually is a combination between two trends. One is the vertical trends, the other one is the horizontal trends. The vertical trends, top to bottom, is getting smaller, and from right to the left is also getting smaller, right? Those two trends combined together, making the overall trends is top right is the largest, and the bottom left is the smallest. Okay, yeah. So generally, this is what we talk about for the review about what we talked about last time. So today we're going to focus on the Lewis structure. Okay, we're going to focus on Lewis structure. How many of you have already learned the Lewis structure before? You heard of the Lewis structure? Okay, yeah. Let's keep continue talk about in more detail. Okay, so before we talk about Lewis structure, we need to talk about one more concept. It's called the valence electron. This is a very important concept. Before we when we write the Lewis structure, which is called a valence electron. So what exactly is a valence electron? The definition is talk about is a number of electrons. Number of electrons in the outermost shell. So the number of electrons in the outermost shell. Okay, so what does that mean? Let's just make some of the example, like oxygen. Right? Oxygen has 8 valence electron, has 80 electrons. So there are going to be 1s2, 2s2, 2p6, 2p4. Anyway, yeah, 2p6. So this is the electron configuration for the oxygen, right? Outermost shell, this guy has a 1s2 and a 2s2, 2p. So you're talking about the shell, they have 2 shells, right? The outermost shell is the second shell. So how many number of electrons in the second shell is the valence electron, okay? So this guy has a 6 electron in the outermost shell, then the valence electron for the oxygen is a 6. So this guy has a 6 valence electron. Okay, so this guy has a 6 valence electron. Okay, then if we talk about sulfur, okay, if we talk about sulfur, sulfur has 16 electrons. And then the electron configuration is a 1s2, 2s2, 2p6, 3s2, and 3p4. So that is the sulfur. And you're talking about sulfur over here. They have three shells, right? 1, 2, and 3. So the third shell is the outermost shell. How many electrons in this sulfur? 2 plus 4. It also has a 6 valence electron. So this guy, sulfur, also has a 6 valence electron. Okay. And if you're looking at the next one, is selenium. Selenium. This guy has 34 electrons. So the valence the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4, 4p4. Right, if you're looking at the 2 to 6, that's 10, 20, 30, 34. Okay, yeah. So this is the electron configuration for selenium. And then just make sure this guy has 4 different shells. First, second, third. Third. And the outermost shell is the fourth shell. You see, although 3D is right in between the 4s and 4p, but the 3D is still in the third shell. It's not in the 3D is not in the outermost shell. Okay. The reason we're writing like this is because we're writing the electron configuration is based on the order of the energy. Okay. So 4s has a less energy than the 3D. So you put the 3D in the middle. But it doesn't mean 3D is in the fourth shell. 3D is still in the third shell. Okay, 3D is still in the third shell. So the outermost shell for the selenium is 4s. So that's why this guy also has a 6 valence electron. That makes sense, right? Okay. So this is what we talk about valence electron. And you see, if we have same elements in the same group, usually they are going, not usually, they always has the same valence electron. And that is why we group them together. And usually, same number of the valence electron for the elements will give you the same similar chemical properties. Okay, because the valence electron is in the outermost shell. Those electrons is the most active electrons. They are going to, when we do the chemical reaction, those electrons is the most active one. Okay, so they are going to pair with other gain the electron or lose those electrons. So that's why those are, as long as you have the similar valence electron, they are going to have a similar chemical reaction. Okay, so this is the valence electron. Once we know the valence electron, well, we can easily to determine the Lewis structure. But just to let you know, when we talk about the valence electron, you don't have to always draw the electron configuration to figure out the valence electron. Just need to remember the group number. So we're not talking about the complete metal. We don't have to worry about that part. We're only talking about those main group. Okay, main group has 8 columns, right? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 columns, and then we're going to have 8 different valence electrons. One group has 1 valence electron, 2 has 2. 8 group, 8A has 8 valence electron, and no more than 8. Okay, usually when we come to the valence electron for those elements, no more than 8. Okay, no more than 8. Okay, so now let's talk about the Lewis structure. So when we talk about Lewis structure, let's start from easier one to the harder one. The easier one, let's just talk about how to assign the electron configuration for how to do the Lewis structure for element. Okay, so for example, the sodium. sodium is a 1A group. So this guy only have a one valence electron. In another word, you just need to assign one dot in the outside of sodium. Okay. So how many valence electron means how many dots you need to put in the outside of this. So that's why you just write a sodium, then you put a one dot in the outside. That's it. It really doesn't matter where you put the dot it is. You can put the dots on the top, you can put it on the left, it really doesn't matter, or you put it on the bottom. That's fine. But usually people do this and this. Okay, usually people do this or that. But it doesn't matter which one you got. And if you're talking about like that's the sodium. If we talk about aluminum, aluminum is a 3A group. So this guy has a 3 valence electron. And again, if you assign the more dots, we need to assign one single dot on each side of this elements. Usually the elements has a 4 side, right? This guy has 4 sides. So you're going to put one single dot on each side first. So aluminum, you just put aluminum, then you put the 3 dots. That's it. Doesn't matter which part you're at, you always, okay? So as long as you have a 3 single dots in the outside for aluminum, that's it, okay? Yeah, again, for the elements, you always put the single dots first. For elements, you always put the single dots. For the nitrogen, this guy is 5A group, so they have 5 valence electron. To assign 5, then again, you put the 4, you put a 1 on each side first. Since we have a 1 more, right? Then the other one have to paired with another electron. Doesn't matter pair which side you pair, but you're gonna have one pair, one side is a paired, the other 3 are unpaired. So this is the Lewis structure for nitrogen. That makes sense, right? And we're giving the different name for those dots. If you're talking about the single dots, that's called the unpaired electron. The unpaired electron. And if this guy has a pairs, it's a paired electron, and we call this paired electron is called a lone pair. Lone pair, that means this guy lonely. They're not going to react with other stuff. As long as it's paired, that means it's already stable. So the most effective one is on those unpaired electrons. Okay, those are unpaired electrons because they would like to pair. And remember, those paired electrons is in the box. The paired electron, for example, so the nitrogen, right? Nitrogen is 1s2, 2s2, 2p5, 2p3. So it's a 1 box, 2 box, and 3 box. 1s, 2s, 2p. So this guy has a 1s, 2s, and 3p. You see, those are 3 single dots. Is actually on the 2p, and those paired actually is the 2s. So the most reactive part is still on the single electrons. Those single electrons would like to pair with another electrons, then to be stable. So that's why those are most active one. Those are 2s electron is already paired, so they're not going to participate in any of the reactions. All right. So that is the Lewis structure for the single elements. Okay. Okay, so now go ahead to write down what is the Lewis structure for chlorine. Okay, so first of all, chlorine has 7 valence electron. It's a 7A group, right? So this guy has 7, so you put 4 on side. And then you have 3 more, so you have to have 3 paired electrons, lone pairs, and 1 single unpaired electron. Then that's gonna be the electron configuration. Sorry, that's a Lewis structure for chlorine. Okay, so now we talk about the elements. Then we're going to talk about iron, how to write the iron. Okay, how to write the iron. For example, if we have the chlorine, right? We know the chlorine, chloride ion. How to write the chloride ion? Well, then you need to know how many electrons, valence electrons for the chloride ion. We know the chlorine has 7 valence electron, right? And then here they gain 1 more electron. So totally they are going to have 8 valence electron. That makes sense, right? This guy has 8 valence electron. So you should add 8 dots instead of 7 dots in the outside for the chlorine, for the chloride ion. So that's why you write the chlorine, and you put 8 dots on the outside. The 8 dots means the area is already opaque. Okay. We shouldn't have more than 8. And this is also what we talk about. It's called the octet rule. Octet rule. Okay. So this guy, we write 80 electrons. Then you need to write a bracket and put the sign, the charge in the outside. This is the difference between the chlorine elements and the chloride ion. Okay, this guy has chlorine has 7 dots. We say 7 dots. Chloride has 8 dots. Since they gain 1 more dots, so they have a negative charge shown over there. Okay, and you have to, if you have a dots and a charge, then you have to using brackets to separate the charge and the dots. Okay, this is very important. Remember, this signage is developed before we have a computer. Okay, so everything is handwritten. If you don't have the brackets, then if you have something, maybe you say you put a. If you have something on the side, how can you tell whether this is a dot or a sign or a negative sign, right? So that is why the most important, if they have a dot shows up there, you have to have a bracket to separate the sign and the dots. Are you clear? Okay, very important, this part. Okay, yeah. Then again, if you're right, okay, how about the nitrogen, nitride ion? Nitride ion, again, nitride has 5 valence electrons, and then you gain 3 electrons. So they totally has 8 valence electrons in total. In another word, this guy should have 8 dots in the outside, and then you're gonna have a bracket and put the 3 in the out, 3 negative in the outside. That makes sense? Right, so this is the negative ion, which is anion. So when we do the cation, it's much easier. For example, sodium ion. How do we write a sodium ion? And we know sodium, they only have 1 dot in the outside. Since the sodium ion, they're losing 1 dot, right? So this dot is gone. Then, since this dot is gone, then just put the positive. That's it. So this is the Lewis structure for the cation. And then you may ask, do I need to put 8 of the electrons around the sodium? No, we don't have to. Although, yes, they lose the outside, the electrons, then the inside, it has 8. Yes. But usually we're not writing the cation like that. Okay. So once the dot is losing, you just write the charge. That's it. Okay, and meanwhile, you see what's the difference? Although those are all ions, but this one has a bracket, this one do not have a bracket, right? That's because we don't have a dot. We didn't write the dots in the outside of the sodium, so you don't have to write the bracket. So the cations is always easier, right? If you write the calcium usually has two dots, right? And then they're losing the two dots, it become a calcium ion. Then that's it. This is the Lewis structure for the calcium ion. Are you clear? Okay. Then the next one, how can we write the Lewis structure for the ionic compounds? How to write the Lewis structure for ionic compounds? And when we write the ionic compounds, for example, the easiest one, sodium chloride. And in general, we talk about the difference between ionic compound and molecular compound. Is ionic compound is made by ion, by the cation and anion, right? So there have the ionic force, which is the electronic force between the positive charge one and the negative charge one. Then they bind together. So when you write the Lewis structure, you just need to write what is the form for the cation and what is the form for the anion. Then you put them together. That's it. Okay. So for the sodium chloride, then that's just a sodium ion plus a chloride ion. That's it, right? So if you know the sodium ion, then that's a sodium ion. For the chloride ion, this is a chloride ion. Put them together, then this is what we call the sodium chloride, the Lewis structure for the sodium chloride. And they represent each of this has a positive charge. One has a positive charge, one has a negative charge. You have to show the charge. Okay. So now we're writing this as a single elements, right? Each of those are single elements. How about if we write the more, for example, if we write calcium chloride, what are we gonna do? Calcium chloride. Then in this case, we have three elements over there, right? Two chlorides, one calcium. So now, again, when you write the Lewis structure for this one, you're still going to write the cations and anions. But in this case, you're gonna have one more need to concern because you need to find which one is a central atom, which one is a side atoms. Central atom is the one that shows only once, and the side atoms has a multiple, right? So obviously calcium is a central atom. In another word, you just write the calcium in the right middle, right in the middle. And chloride is a side atom, then you put the chloride on the side. Okay, and then you're going to write what is the Lewis structure. Well, what is the formula for, what is the Lewis structure for chloride ion? What is the Lewis structure for calcium ion? That's it, right? So the calcium has a two positive charge, then that is the Lewis structure for the calcium. And the chlorides is this, and this chloride is this. That's it. That's gonna be the Lewis structure for the calcium chlorides. Okay, so once again, later you may be confused. Okay, what kind of formula we're gonna write? But you need to make sure we're writing is ionic compound. We haven't touched the molecular compound yet. So when you write the Lewis structure, you need to identify, is this an ionic compound or is this a molecular compound first? And then you, based on the rule, you write. Okay. Any questions? Okay. So now let's think about how to write the aluminum chloride. Well, generally it's the same thing, right? So you're gonna write the aluminum in the middle. Write the aluminum in the middle, right? And then we have free of chlorides. Now think about where should we write the chloride? On the side, we have 1 chloride, 2 chlorides, 3 chlorides. Okay, and then I'm gonna write aluminum has a 3 positive charge, and chloride ion is something like that. And that's it. This is the Lewis structure for aluminum chloride. Make sense? Make sense? Okay. All right. Then could you write the Lewis structure for calcium oxide? Okay, so calcium oxide, you see, we have a 1 calcium and a 1 oxygen, right? So in another word, it's just like the sodium chloride, right? You write a calcium and write oxygen, and then those must be the ion, right? Calcium ion and plus oxide ion. So calcium ion is a calcium 2 plus. Oxygen, that's oxide ion, right? Again, oxygen has a 6 valence electron, and this guy has a 2 more, gain 2 more electrons. So they're going to 8 valence electron in the outside. So you're going to have the 8 valence electrons for the oxygen, and then what's the charge? 2 minus. So that's it. This is calcium oxide. That makes sense, right? Calcium oxide. Okay, so how about the potassium oxide? How about potassium oxide? Make sure which one is the central atom, which one is the side atoms. Potassium oxide, you see, potassium, that's 2 potassium. Oxygen is 1. So oxygen here, that's going to be in the central atom. And the potassium will be on the side, right? And then what is the oxide ion? That's 8 dots. And have a 2 negative charge. For the potassium, since they are losing 1 electron, become a positive charge. So that's those are just the Lewis structure for the potassium, and then you combine together, that's it. That's gonna be the K2O. So potassium oxide. Make sense? Make sense? Okay. All right, so now let's take a break. And we already talked about the ionic compound Lewis structure. Now we're going to touch the big meat for today, which is the Lewis structure for the molecular compounds. Okay, let's take a break. Okay, so let's talk about the Lewis structure for molecular compounds. Okay, Lewis structure for molecular compounds. Well, the molecular compound is very different. So we need to talk a little bit. Let's just give you one of the example over here. Okay, so someday we have a two hydrogen work on the street, and this hydrogen said, "Hey brother, how are you doing?" And I'm good. Yeah. Okay, so I'm tough now. So could you borrow me one of the electrons so I will be safe? Then this guy said, no way. I also need one electron so I can be safe. Okay. So they both are short of the one of the electrons. So they want to have one electron and then those will be stable. But none of this would like to give the electrons. So then they're fight together. Okay. So, but they're equal, so they cannot gain. Any of them cannot gain the electron. So they have to, find a way, right? Otherwise there's no conclusion. They have to solve the problem. So that's why the hydrogen said, the one on the left said, okay, so how about I'm going to give one electron and you're going to give one electron. So we have two electrons. And now these two electrons is not belong to me and also not belong to you, but it belong to us. It's belong to us. So instead, they gain the electron. They are sharing the electron. Okay. So this is very important. They are sharing electron instead of gain or lose the electron. So that is the very important difference between the ionic compound and the molecular compound. Ionic compound, the reason they have a positive charge and negative charge is because the electron they need is completely gain or lose, right? If they gain the electron, they become a negative charge. If you lose the electron, they become a negative charge, a positive charge. Then they are making the structure. But this guy, they are sharing electron. They are not losing or gain. So none of this has a charge. That makes sense, right? None of this has a charge. Instead of those two electrons, it's not belong to any of them. It's belong to the both. In another word, those electrons is going to orbit around the two atoms instead of one. Okay? Yeah, so those two electrons is orbit around the two electrons instead of one. So they're definitely sharing those two electrons altogether. Okay? Yeah. That makes sense? Okay? So once they share the electron, then the shared electrons will become a bond. And this is what we call the single bond. Okay? One paired shared electron will form a bond. It's called a single bond. Okay? This is called a single bond. And also, we also have a double bonds, which means they are sharing two pairs of electrons. One of the example is oxygen. You see, for the single oxygen, they only have 6 valence electrons, which means they have two shorts, right? Each of the oxygen has 2 shorts. So if both oxygen atoms would like to be stable, they need to gain 2 electrons. But none of this would like to give. Instead, they are going to share those 4 electrons together, making 2 paired electrons. And those 2 paired electrons will making double bonds. Those 2 paired electrons will making double bonds. So that's why we have the we have O2. You see, we have O2. Then we have H2. That's why you see those gas. Those gas are diatomic elements because this is the most stable form, right? We talk about those are most stable form. They have a 2 combined together. They will be stable. And also we are having a triple bonds. The triple bonds is made. One example is just nitrogen, right? we already know what is the Lewis structure for nitrogen. Nitrogen has 3 unpaired electrons. So those 3 unpaired electron would like to pair with others. So each of the nitrogen need 3 electrons, but none of this would like to give. Instead, they're going to share all of those 6 electrons to making 6 paired electrons, and those 6 paired electrons will making triple bonds. We're making a triple bonds. And so that's why we have N2, right? We have N2. And another elements, so remember, we have F2, Cl2, I2, and Br2. Remember, right? We have a totally 7 of those elements are diatomic. The reason they're going to form like this, remember, fluorine, each of the fluorine has a 7, and this fluorine also has a 7, right? So now they only just need 1 electrons to pair, but none of this would like to give. So instead, the giving or gain or lose, they are having a 1 paired electrons between each of the atoms. Then this will become a single bonds. And that is why we have F2. And Cl2, I2, Br2 generally is the same thing, right? Because they all have the 7 valence electron. So they're going to build the same thing. So that's why F2, H2, O2, N2, and others those are most stable form, because they just need this 2 combined together will make them most stable. That makes sense, right? Okay, so that is what happened for the Lewis structure. They combine together, they share the electrons, making single bonds, double bond, and triple bonds. Okay, yeah. And by the way, this is the out-topic thing. You know, this, and this in Chinese, that means something. You know what is that? 1, 2, 3. Yeah. So this is 1. This is 1, this is 2, this is 1, this is 2, this is 3. Okay, but don't think about the 4 is 4 lines. Okay, 4 is not 4 lines. There's a different letter, but at least you have 1, 2, 3. You know 3 characters. Congratulations. Okay. All right. So now this is a Lewis structure for molecular compounds, but then since there's a lot of the Lewis structure for the molecular compounds, how do we assign the dots just based on the formula? Then this is the topic we're going to talk about. Okay, so let's go the easy way, easy thing, CH4. This is methane. How do we write the Lewis structure for methane? Generally, there's several steps. The step 1, you need to find how many valence electrons for this molecule. Okay, to find a valence electron, you just need to add up the valence electron for each of the elements plus the charge. And since this guy has no charge, it's a compound, so you don't have to add anything, but you just need to add the elements, a valence electron for each of the elements, right? The carbon is a 4A group, so this guy has a 4 valence electron, and the hydrogen is a 1A, so you have a 1, but they have a 4 of hydrogen, so you got time 4. So that's minus, totally this guy has 8 valence electron, right? They have 8 valence electron. Then what are you gonna do? If this guy has 8, then that means you need to assign 8 dots around it. Okay, you need to assign 8 dots in. And then you're gonna find which one is the central atom, which one is the side atom. Central atom is in the right in the middle, side atom on the side, hydrogen on the side. Okay, then what are you gonna do? You're going to first put the 2 dots, which is the shared electrons between the elements, right? You have to, otherwise they're not going to bond together. Since they have a bond, because they are shared electrons. So we're going to, at least, we're going to put 2 on each side. First, don't worry about the double bonds or triple bonds. The first thought is we're going to just have a single bond first, okay? And in some other case, we will think about the double bonds or triple bonds. But before, first thought is a single bond. Okay, so now we put those four on the outside. Four pairs of the electrons on each side. Then looks like we already have 8. Then we don't have to do anything. But once you're assigned all the dots, you need to double check. Well, are all elements follow the rules? Okay, we talk about the octet rule. And then there's another rule, it's called the duet. The duet rule, octet rule, let's talk about the duet rule only follow the rule is hydrogen and helium. Hydrogen, if the hydrogen only usually has one dot, right? If they have 2 dots, they have to be paired dots, because in the 1A group, right? In the 1S, the first row, they only have 2 electrons. So those 2 electrons have to be paired. Okay. If the first period has 2 electrons, those 2 electrons have to be paired. Helium is the same thing. The helium is a paired electrons. The hydrogen, if it has 2 electrons, they have to be paired. So this is a hydrogen and helium, they follow duet. Octet is talk about the elements other than helium and hydrogen. So this helium already duet, this one duet, this is duet, this is also duet. And if you talk about carbon, carbon is octet. It's octet, right? So that is why now that means this formula is perfect. This structure is perfect. Everyone follow the rule, and we already have the 8 dots around. So the last part is you just get rid of those shared electron and making a dash as a bond. So now the Lewis structure for the methane will be like this: 1 carbon and 4 side hydrogen, and then you have a 4 dash around it. Then that's it. This is a Lewis structure for methane. Pretty straightforward, right? Okay, and then let's go a little bit more. Okay, so water. The water, again, if you're looking at the valence electron, they have a 1 times 2. Oxygen has 6. Totally, they have 8 valence electrons. So we need to assign 8 dots. Central atom is oxygen. Oxygen in right middle. Hydrogen, that's on the side. Okay, so now we're gonna have 8 electrons. So we're going to put the shared electron in the middle. And you see we have 4 dots. And we have 4 more dots to go. And if you're looking at the side hydrogen can only have 2. So now the hydrogen is already fully filled. So if the side atom is fully filled, then the actual electron will go for the central. Okay? And remember, I don't want you to be confused. When we assign the dots on the elements, we put the single dots. Right? Remember? But if we put the dots on the molecule, then we always put the paired dots over there. We always put the paired dots. Okay? When we assign the dots on the molecule, we always put the paired dots. So that's why you're gonna put the 2 paired dots on the oxygen. Then you check, okay, so oxygen has 8, hydrogen has 2. Then this is a Lewis structure for the water. So that's why this is the Lewis structure for water. That's it. Okay, this is a Lewis structure for water. All right, so now go ahead to write the Lewis structure for PCl3. Okay, PCl3. Okay, so the PCl4 first, how many valence electron for this guy? Phosphor has a 5 valence electron, chlorine has a 7, so 7 times 3. Totally 21 plus 5, you have a 26 valence electron in total. So you're gonna assign 26 dots. Well, which one is the central atom? So obviously phosphorus is the central atom, and chlorine is the side. Okay, now to assign the dots, it's better to assign the dots on the side first. Okay, and this is usually the rule because the side atoms always follow the octet. Later we will talk about some exception. The exception only happens in the central atom. On the side atom, always follow the octet. So there's it's okay if you assign the dots on the left side, on the outside first. But before that, we're going to put the 3 paired the shared electrons, and then we're going to assign the dots on the outside. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now, you see, I put the 24. Once we put the 24, then the side atoms are 4. Then we have 2 more to go. Then the 2 more have to belong to the central atom. Okay, so now if you double check, chlorine has 8, 8, 8, and phosphorus has 8. So everything has 8 now is good. Instead of then you're going to get rid of those shared electrons, then you're making up single bonds, and that's it. So that's gonna be the Lewis structure for the PCl3. That's phosphorus trichloride. Phosphorus trichloride. That makes sense now? Okay, yeah. So now you see, those are just assigned the single bonds. But how about if we have a case where we find the double bonds? Okay, if we assign the double bonds, for example, we have the CO2. Okay, CO2 carbon dioxide. For the carbon dioxide, then you see carbon has a 4 valence electron, oxygen 6, times 2. So that's a 16 in total. 16 valence electron. Again, carbon should be in the central and the oxygen on the side. And then again, we put 2 paired electron as a shared electron. Then we're going to assign more. So I prefer, again, we're going to go for the side atoms first. So now we have a 4, then 6, 4, 6, 8, 10, 12, 14, 16. Okay, so now once we assign this, it's become 16, right? Now it's done. Then you will see oxygen has 8, but carbon only has 3, right? Carbon only has 3. Oh, I only have 4 electrons, which means this is not a good Lewis structure. Which is the Lewis structure for carbon shouldn't write like this. You shouldn't write a Lewis structure for oxygen like this. This doesn't work, okay? Because the central atom only has 4 electrons. This is not follow the rule. Because we talk about we should have octet for all of the elements. But right now carbon only have 4. So this is not correct. Okay. Now you need to think about, okay, so to make this to make the carbon as has 8 of the electrons, then we have to transfer some of the lone pairs to the shared area, right? Where are the lone pairs? I mean, those are lone pairs, right? Those are the lone pairs. So we need to think about we need to move those lone pairs to the shared area, right? So you can, there's 2 different ways to do this. You can move one shared on the oxygen on the left side, or put one lone pairs to from the right side to the shared area. Then you will see something like that. Makes sense, right? So now you can see now oxygen over here, there's still 8 dots. This oxygen still 8 dots. And the central atom, the carbon has 8, right? 4 on the left side, 4 on the right side. So you have 8. So this guy follow the octet. Then that's going to be the correct Lewis structure, which is we have 2 double bonds on each side. 1 double bond on each side of carbon. And then you can write the leftover of the molecule, the electron. Then that's it. This is a Lewis structure, right? And there's another way to write, which is you put like 2 pairs on one side to the shared area, and then the other side you don't have to put anything, right? So then you're going to have a 1 double bond, 1 single bond, and 1 triple bonds. This, if you're talking about this guy, this is also follow the octet. But just to let you know, in nature, molecule, if the molecule can be symmetric, it will go for symmetric. Okay, yeah. And later we will talk about one of the concepts. It's called the formal charge. And the formal charge will help us to determine which structure is correct or not. Okay, but just to let you know, this one is the correct structure, but this one is not correct. But just to let you know, but this one still follow the rule, but this is not a correct structure. In nature, they're not going to making this structure. This structure is not stable. Okay, yeah. All right, so this is the Lewis structure for the molecular compounds. Okay, Lewis structure for the molecular compounds. And if we talk about for some of the ions, like the molecular compound, the polyatomic ion, we can also write a Lewis structure, like a CO3 2-. So this is a carbonate ion. Carbonate ion can also write a Lewis structure. And just to let you know, this guy, you see, they have a carbon and oxygen. This is a non-metal plus non-metal. So inside of the CO3, this building, they are having a molecular bond. They have a covalent bond over there. So this guy still have a covalent bond over there, but there just has a charge. So you can also write a Lewis structure, something like that. Okay, the carbon has a 4 valence electron, oxygen has a 6 times 3. This is how much valence electron belong to each of the elements. And then you're gonna remember, they are also including the charge. Since this guy has 2 more electron, they gain 2 more electron. So when you write the valence electron, you're gonna gain 2 more over there. So 4 plus 6 times 3 plus 2. Then this is how much the total valence electron for this guy. 18 plus 4, 24, 22 plus 2, that's 24. So we have a 24 valence electron for this compound, for this polyatomic ion. Then carbon in the right middle, oxygen on the side, still follow the octet. And then it's the same thing. The only difference is, okay, later when you write this, you need to have a -2 charge of there, right? And because this guy has a charge. And in the middle, again, you're going to assign 24 dots. We're doing the same thing. First, we put 3 pairs shared electron, and then we assign the dots for the side atom. So 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Okay, now you see, we only have a 24. So once you're assigned that much, then you're done. We're not having enough. right? We are having enough for the side atoms, but not having enough for the carbon. Carbon only has 6. So you see, when we short of the electron, that's gonna be the time that we think about double bonds or triple bonds. So never start with a double bonds or triple bonds. Okay, we always start with a single bonds. But when you're assigned the dots, you're short of the dots, then you think about that's gonna be a time we're thinking about double bonds or triple bonds. Are you clear? Okay. So now you see this guy is short of only 2 electrons. So you only just need to move one lone pairs to the shared electron, then we're done, right? So it doesn't matter which one you have a shared electron, they are all fine. So let's just go for this one, right? You move this one to the shared area, then this carbon will be octet. That means this guy has a 1 double bonds, 2 single bonds shows up there. So 1 double and 2 single. And then you have the -2 charge. Well, then if you're talking about, is that possible? Is that okay for this one? Yeah, that's okay if you write it like this. Then how about, is this okay for this one? Yes, this is also okay. And just to let you know, those 3 structure are generally the same. Okay, those 3 structure is the same. We're giving those 3 structure a name. It's called the resonance structure. It's called the resonance structure because those are the same. And in general, typically, this is like a short parts for the Lewis structure. Lewis structure cannot write, either they write a single bond or double bond or triple bonds. That's a whole number, 1, 2, 3, right? But for this structure, actually, each of the oxygen combined with carbon actually is not completely a whole number of the bonds. They are sharing the 3 atoms sharing 4 bonds. 3 atoms sharing 4 bonds. So each of the atom sharing 4/3 bonds. Okay, but when in the Lewis structure we cannot write. So then we are going to write the resonance structure of this. So in general, those are not exactly as 2 bonds. This one is not exactly 1 bonds. They are sharing a little bit of 1 plus 1 1/3. 1 1/3 of the bonds for each. Okay, but in the Lewis structure we cannot write. Then we just write like this, and this is what we call the resonance structure. Resonance structure. A lot of those polyatomic ion will have this kind of structure. Okay, but you don't have to worry too much about this. We usually talk about more in the organic chemistry. Okay, on this part. All right, so this is the Lewis structure for the ion. For the polyatomic ion. The last part, we're going to write the exception. So exception, that means, right, we talk about octets or duets. The exception is this formula may not follow the octet. They may not follow octet, especially for the central atom. And again, side atoms always follow the octet. Okay, side atoms always follow octet. So one example is a BF3. So this is a boron trifluoride. So boron trifluoride, boron has a short electrons in the middle. This guy has only 6 electrons for boron. This is a correct Lewis structure for boron trifluoride. You see, the boron only has 3 bonds, which means a 6 valence electron over there. And but this is the correct formula. Okay, this is the correct formula. So that's why the boron trifluoride is short of electron. But most of the case is we have more electron. Okay, for example, the PCl5. Okay, phosphorus pentachloride. Okay, phosphorus pentachloride. And if you're looking at this guy has 5 and has 7 times 5. Totally, they have a 40 valence electron. So we're gonna have a phosphorus, and we have a 5 of the side atoms. And if you're looking at only just the shared electron, phosphorus already have 10, right? So this guy, if you put the 10 shared electrons, this guy already have a 10, which is not follow the octet. But this is what we have to write. Then you assign each of this, right? The 10, 20, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Now, you assign everything, all the valence electrons of there. Then you will see this guy has 5 bonds for the central atom, but the side atoms are still follow the octet, but only the central atom not follow. They have extra dots, but this is also this is normal. I mean, we have a lot of the man-made. The structure is something like that. Okay. In nature, they also have some of the particle, but not so many. Okay, so this is the Lewis structure. And if we talk about one more, so let's see the xenon tetrafluoride. See, again, we talk about xenon is a noble gas. Xenon is not going to react with others. So this is a man-made compound. Naturally, it won't going to happen. Okay, xenon tetrafluoride. And if you're looking at the Lewis structure, xenon has 8 valence electron, fluoride has 7 times 4. So you have a 28 plus 6, that's a 36 valence electron. Then we're going to assign 36 of there. So xenon in the central, and we have 4 of the fluorines. And then put the shared electrons, that's 8. Then we're going to assign the side atoms, 8, 10, 12, 14, 18, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so now once we assign all the dots around the side atom, we do 32. So we have 4 more to go. Okay, again, side atoms can only have octet, only follow octet. You shouldn't add more on the side atom. So the 4 atoms should go to the central atom. Okay, should go to the central atom. And again, if we have 4 dots, once you're assigned the dots, 4 dots, extra dots in the central atom, we always go for the paired electrons. Okay, we always go for the paired electrons. So that means we need to put 2 more paired electrons over there. Well, it doesn't matter where you put. So I'm going to just put 2 over here, 1 pair over here, 1 pair of the other side. Then you get rid of those shared electrons. Then that's going to be the Lewis structure for the xenon tetrafluoride. Xenon tetrafluoride. Then you will see this guy, xenon, has 10 electrons around it. No, they have 12 electrons around it. 4 bonds and 4 lone pairs. 4 bonds and 2 lone pairs. So that's going to be the Lewis structure for the xenon tetrafluoride. That makes sense? Okay. Yeah, I would like you to do some of the practice before we do some other. So let's turn to the practice study guides, page 18. Page 18. So I would like to you work on the question. So here is all for the Lewis structure. Okay. So page 18. So go for the E, the formula E, formula F. So formula E, formula F, then G, then N, then P. Okay, so E, F, G, N, and P. E, F, G, N, and P. Make sure counts the valence electrons, number of valence electrons first. important. Okay, we're going to review those Lewis structures. And again, for the rest of those questions, you can work on after the class. So question number, so the E, SF2. So sulfur difluoride. Again, valency electron, how many they have? Sulfur has 6, and fluorine has 7, 8 times 2. So 14, totally we have 20 valence electron. 20 valence electron, then sulfur in the central, fluoride on the side. Again, first of all, you're gonna write a pair, the shared electrons, because you have to have a shared electrons to making a bond. That makes sense, right? You have to have it, otherwise they're not going to form a molecule. So you have to have a shared electron first between each of this. And again, the shared electron means one single bond. And then you're going to assign the dots on the side atoms first, okay? Because side atoms always follow the octet. So now we have 4 now, 6, 8, 12, 10, 12, 14, 16. So now you have a 16. And we have a 20. So we got 4 more to go. Where are the 4 to go? Well, the side atoms are already at 8. So you shouldn't add more on the side atom. Instead, just put the dots in the center. Okay. The central atom right now, the sulfur only have 4. So you need the extra, right? And we put 1 pair on the top, 1 pair on the bottom. Okay. You may think about why I cannot put the dot, why cannot I put it like this? Well, the point is, we talk about, right, you have to, since this guy has a 4 side, you have to fill the 4 side first. If they have extra, then the extra will be anywhere else. So since this fluorine haven't filled the 4 sides, then please don't write like this, okay? The Lewis structure, you're gonna put the 2 on the top and the 2 in the bottom. Then you count. So this fluorine has 8, this fluorine has 8, the sulfur has 8 too. Now that's gonna be the Lewis structure for the structure. And get rid of those paired shared electrons and making a double bond. That's it, okay? The reason we're writing the shared electron because the shared electron is a single bond, okay? Are you clear? And the shared electron also counts, the single bonds also count the dots, okay? Not just write the dots, the single bonds also count dots. Each of the single bond counts 2 dots. Single bond 2 dots, double bonds 4 dots, 2 bonds 6 dots. Okay, so this is a SF2. Then SF4. So we have 6 plus 7 times 4. So 34 in total. So sulfur in the middle, fluorine on the side, and still follow the same rule. Okay, we're going to add 1 pairs of the shared electrons in between each of the atoms. Okay, shared electron. And then let's just assign more on the side. So 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 26, 28, 30, 32. Okay, so now we put 8 on each side, then we have a 32. But this guy has a 34, right? That means we need to have an extra. And where the extra go? Central atom. Okay. Do not write the double bonds. Double bonds is still there. The double bonds is still containing 4 dots, right? It's not you're writing double bonds, then the dots is gone. No, the double bond is still being counted as a dots. So you get rid of this guy, the shared electrons, making 4 bonds. And again, we still have a 32. Then you just put the 2 more on the central. Then that's it. Doesn't matter whether you put it on the right side or put on the left side. It doesn't matter. Okay, as long as you have another 1 pairs of the electron, then that's it. This is SF4. So for the SF6, then again, this guy has a 6 plus 6 times 7. So you have 48 valence electron. And then sulfur in the middle. Then again, you write the shared electrons between the atoms, right? And then you can start to assign more dots. So we have 12 now. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 30, 40, and 42. Wait, 42, yeah, 40, 44, 46, and 48. Now, I put all the 8 electrons around to the side, and then we already got 48. So we no more dots to assign, and then you see every side atoms are full of the octet except the central. Central has a 6 pairs of the shared electrons. And this is what we have to write, right? Otherwise, we cannot make a compound. Then you just replace the shared electrons to the side, to the bond. Then that's it. That's gonna be the Lewis structure for the SF6. Does it make sense? Okay, so the next one is ClF3. Again, how many we have? 7 plus 7 times 3. So we have a 28 over here. Now, chlorine is in the central, fluoride on the side. And again, we're gonna put two dots between the atoms, right? Then we have put the extra on the side. 6, 8, 10, 12, 14, 16, 18, 20, 22, 20, 24. So now we got 24 over here, right? 24, but we have 4 more to go. And these 4 more have to belong to the central atom, right? So now you can get rid of those shared electrons. And then you write 4. So now we have 26 and we have 28. So that's going to be the Lewis structure for the ClF3. The ClF3. And some of you may think about, wait, why can I have the double bonds? And in this case, I don't have to write the extra. But if you write the double bonds, then how about this fluorine? This fluorine, if you count the double bonds here, that means we have extra 4, and then they are having 6 dots. So totally fluorine has 10 now. It doesn't matter. Then that doesn't make sense, right? Because we talk about the side atom always follow 8 electrons. So this is impossible for fluorine because it's already extra. I mean, this is not an exception because central atom only, if we have exception, only for the central. So fluorine cannot have a double bonds. Instead of they are having just a single bonds. And then you put extra in the center. That's it. And xenon difluoride is the same thing. 8 plus 7 times 2. So you have 14. That's 22. You have 22 valence electron. Then xenon in the middle. Fluoride, fluorine on the side. Okay, so now we put the 2 single. Two pairs in the share the area, and then we assign more. So 4, 6, 8, 10, 14, 16. Now we have a 16, right? 16. Now all the fluorine are done, and we have a 6 more to go. Where the 6? The 6 have to belong to the central, right? Then we have an extra to write. That's it. You get rid of those shared area as a bond. Then you will see the xenon has 2 single bonds and 3 lone pairs. That's it. That makes sense, right? Okay. All right. So let's take a break. I will bring the practice for you. And today we're going to work on the practice for the unit 1 and unit 2 content. A little bit unit 3, but most of it is unit 1 content. Okay. Okay, so that is the practice that I print out from the ACS practice. In general, final is the ACS, the American Society of Chemistry, yeah, assessment. So this is a similar practice like the final. So that's why I would like to do the practice of it. And just so you know, the first several page is just an instruction about how the similar pattern and the rest of the problem solving of it, how to solve those patterns. If you have the real practice is in the last several pages. If you see there's a sum of the box like this, it is just telling you how to solve the problem. It's not a real practice. Okay, the practice is it shows after that. If it has a practice, it will show the practice. It shows the practice packet. And then in the end, we have answer. We have an answer. Shows off there. Okay. Yeah. Everything is a multiple choices. Everything is multiple choices. I would like to first work on the conceptual problem. On the side of the question, it will show the that is the real conceptual question. So I would like to work on the conceptual questions. We don't have too many of those conceptual, but you can work on that. And then today we are having 2 worksheets. Then you can work on this. But I would recommend there are too many questions, but you can only just work on the odd number. Not all the odd number. So 1, 3, 5, 7. So just go like this. And because you have a lot of similar questions, so just go all the numbers, then you will have chance to generally cover every questions, every type of the questions that you have. Okay. Yeah. So I'm going to give you 2 of them. One is the chapter 1. The other one is chapter 3. Okay, chapter 1 and chapter 3. Okay, so please come over here and I'm going to have. So just pick one each, chapter 1 and chapter 3. Now the final are all multiple choices.